Hi, everyone. Thank you for joining. I really appreciate it. And today, basically what I'm going to do, I'm going to, well, first of all, can you see my screen?
Yes.
Okay.
Yeah.
So what I'm going to do is go over two examples. One is going to be kind of a mechanical problem where we're maximizing stiffness, and then we have a mass budget. Is the typical topology optimization problem that you see in papers and in other commercial tools. And then the other problem that I'll do one thermal problem where we have an optimization problem where we're maximizing thermal conduction in a part given a set of boundary conditions as well as a mass budget. So I'm going to go over those two examples. And then I also kind of build the geometry that I already built myself and run the problems myself as well. But I'll open Gmesh and then build this simple geometry that I put together just so that you get an idea on how to use Gmesh. Plato is capable of then taking the Gmesh file, and translating it into the format that we need for to run Plato. The format is known as Exodus, and it's a Sandia developed mesh metabase format that is actually open source and widely used. And then I'm going to describe the input files for both examples. So I'll open an input file and kind of go over how you can set up your input files for your problems. And like Professor Hochhalter said, what we're going to do is we'll take your mesh files and those input files, and then we'll run the problem for you. They're installed. Plato is installed on the HPC machines that you have there. But to make life simpler on your end, we'll do that for you. I was hoping to run the problems live so you could actually see how fast the simulations are solved. But sadly, I have to do it on my personal laptop computer and not on my work computer because we're not allowed to use Zoom on my work computer. So I already ran the problems. I'll show the results, and you'll be able to see those in pair view. And but sadly, I'm not able to show you how fast they actually solved. But with that, are there any questions right now?
Yeah, I'm wondering if you could maybe share with us the Gmesh file that you used, or if that's possible.
Yes, it is. And I believe Professor Hochhalter uploaded those onto your class website. And you should be able to download the mesh files as well as the input files that I'm going to go over today.
I'll look for it and see if I can find it.
Yeah, if you're not able to find them, then I'll make a note here, and then we'll make sure to upload those. But I think he was able to do that last night. But if that's not the case, just let us know.
Oh, I found it, and it's the geo file, right?
Yeah, so there's the geo file, and there's the geometry file, and then you can upload that onto with Gmesh, and then you can create your mesh file if you want.
Cool.
Okay. Are there any other questions? All right. If there are no other questions, then let me get going. So to run Plato, like I said on Tuesday, there's two versions of Plato. There's a open source version of Plato, and the open source version of Plato basically has all the algorithms, everything, all the code itself is online. However, that code doesn't come, the open source version doesn't come with a user interface. The government licensed version has a user interface, and then all the technology that is in the open source repository is actually the same technology in the government license code, with the exception of in-house code, physics finite element code called Sierra. However, actually we started Plato using Sierra. That was that's the legacy version of Sierra. But now moving forward, we are actually just using the latest version of Plato, and we are going to, so you're not missing out on any technology other than the user interface, really. And some news here is that we're actually developing a user interface for the open source. So hopefully by this time next year, you should also be able to have a user interface to set up your problems in the open source with the open source code. And actually, let me show you and where the open source code is. And I'll share this with all of you. So here's the Plato website on GitHub. Here are all the tools that we have. So this is the finite element code. This is the optimizer and other modeling tools that we have. And then there are other, those are the main tools, and everything is really in these two directories. Everything else is related to, this is a package that we do use to automate the installation process. And then the other ones are just basically tests. And the last one is our finite element or linear algebra system of equation solver, which was developed by NVIDIA. And is also open source. And that's what we use to solve our system of equations. But really everything of all the Plato code is in here. And let me put this in the chat window so you can actually have access to it. See if I can do this. Chat. Oh, here it is. So there it is. Can you send me as well? Thank you. Okay. Leave this here. So if you later after the class, if you want to explore more, then you can come here and then you can look at the code and everything that we have developed. But for today, to run Plato, really what you need are two input files. There's the computational model file, and that's basically either, in your case, is the mesh file. So that Gmesh mesh file, and then the input deck. Those are the two files that you need. And then what we do is we take that input deck and we take the mesh file and we run a translator that takes the mesh file and puts it into the format that we want and run the simulation. But those are the two files that I'm going to cover today. And I'll start with Gmesh. And I already have my Gmesh open here. And the problem that we're going to be running is fairly simple. Is you can think of it as a cantilever geometry. Is basically 10 feet high or 10 units high and 30 units of length and 10 units of width. So that's the geometry that we're going to build. And then it's going to be fixed on one end, on the left end, and then we're going to apply the load on the right end of the structure. So this geometry, you can come to Gmesh, and then to build your model, you start with the geometry. And then if you come here to this add keyword, there are multiple options that you can select to build different geometries. In our case, we're going to start with something simple, which is we're just going to add the points of this geometry. So if we start with the 0, 0 point, then you click add, and it puts that point right there in the center. And then I'll keep adding the other points, 30, 10. All right. So now I have the points for my bounding box, as you can see. So 10 units high and then 30 units of length. I'm also going to add 2 more points, and that's going to denote the stripped where I'm going to apply the load. So once I extrude the geometry with Gmesh, I'm going to create a stripped, and the load is going to be applied on that stripped surface. So to do that, basically, I'm going to put a point at the end and make it 4.5. You can see it added the point here. And then I'm going to add one more, 5.5. And then I have my bounding box with the strip that I'm going to use to apply the load. Next thing that we do is we're going to create the lines, so connect the points. First line here. All right. So now we have our 2D plane. The next thing that we need to do is we need to define, and there's multiple ways that you can, well, first I'll hit Q to quit out of this option. But the next thing that I'm going to do, I'm going to define a surface. Right now, I do have points and lines connected to those points, but I have not defined a surface. And there's many ways that you can do this. Usually, I use these plane surface options. And with this option, I basically select my 2D geometry. And now I can click E, and then that ends the option. And as you can see, I have defined my plane surface. So now that I have my 2D model or geometry in place, since I'm running a 3D problem, I'm going to use, take this 2D plane and extrude it in the Z direction 10 units so that I can create my bounding box. To do that, you come here to this option, extrude, and I'm going to pick the translate option. So then here, I'm going to say that I'm going to do 10 units in the Z direction. And I need to select all the entities, geometrical entities that I want to extrude. In my case, is all of them. So I select those and I click E. And now you can see my bounding box. And then you see here, this stripped here is where I'm going to apply the load. For both cases, for the mechanical problem, I'll apply a traction force in the Y direction. And then for the thermal problem, I'll apply a thermal flux on this surface. So next, now that we have our bounding box, it's fairly easy to then mesh the geometry using Gmesh. So with Gmesh, there's 3 steps that you need to follow to mesh your geometry. But basically, the first thing that it does is it applies the seeds on your lines. So that's what 1D meshing means. Basically applies the seeding first. Then it builds the surfaces, the triangles on the surfaces. And then finally, you build from the triangulated surface, you then build your volume surface. So Gmesh basically takes a out, kind of like an out-in approach to generate your mesh. First, you generate the external bounding mesh, and then you generate your internal mesh from the external information. So that's how the algorithm works. So let's do that. First, we click 1D. So it did the, you can see finish the 1D meshing. Then now we do the 2D meshing. So it actually triangulated the surfaces and he put the triangles on the surfaces. And then finally, we're going to create the volume mesh. Now, if you want to see a different perspective, right now you're able to see all the lines internal to the geometry, but it's, personally, I don't like that view. It doesn't allow me to see much the quality of the mesh. So you can click on this O option, open menu, and then you can come here, mesh visibility, and then you can click on 2D element faces. And now more or less you can see your geometry and your mesh. Are there any questions right now up to this point? All right, doesn't sound like there's any questions, so I'll continue. Well, this mesh is, you can run a problem with this mesh. It's fairly coarse mesh. I think it has, let me see how many elements. 16,000 elements approximately. It's a fairly coarse mesh for a 3D, like a 3D finite element simulation. So maybe if you were to ask, well, how can I refine the mesh? There's two ways that you can do it. I'll show you the hard way first, and then I'll show you the easy way to do this. The hard way is to basically, one by one, specify the seating on each point. So you can do that in this define option, and then you can use this option here, size, add points. I know, and there's other ways that you can do this, but I'm just going to show you the easiest way of all the hard options. This is the easiest for me. Maybe some of you are more advanced with Gmsh and know other ways to do this better. So here you can select the value of the element size for each point. And then Gmsh, what it's going to do is basically going to interpolate across those 2 points. So if you were to add a larger number here and then a smaller number here, Gmsh, what it's going to do is going to place the element size and it's going to vary it based on some internal algorithm that it has to interpolate the size of the element. In my case, I'm just going to pick a single value, a homogeneous value across the full mesh. So by default, it selects a value of 1. And what that means is a unit of 1. So if I have a length of 30 for this cantilever beam, then if I have an element size of 1, it's going to place 30 elements along the X direction. And in the Y direction, it's going to place 10 elements. And then in the Z direction, it's going to place 10 elements. I want to reduce that by half. So I'm going to say, I'm going to do 0.5. And then I select one by one the points. So now, and then I just click E on my keyboard, and then that's it. And now I repeat the meshing process. I go 1D, 2D, and now it's doing the 3D meshing. And if I were to come here, turn on these options, you can see that my mesh is finer. than the last mesh that I built. Now that's the hard way to do this. The easy way, Gmesh also has a really nice capability where you can actually use a script and type the full problem in a text file and then load that file into Gmesh, and then Gmesh will generate the geometry and the meshing from that file. It basically requires more knowledge about Gmesh, but once you get used to it, it's something that is actually a fairly easy tool to use and also a very convenient tool to use. So to do that, you can come here into, you see this option here, edit script. If you press that option, then see, hopefully it should be opening pretty soon. There it is. So here is the geometry file that Gmesh has been saving as I've been creating my model. Another way to do this and change the mesh is by coming here, and this is X. So if you see the points, this is basically X, Y, Z, and then this is the element size right here. By default, it sets the element size to 1 unit. You can also come here, and then let's say now we're going to change that to 0.4. Actually, let's do 0.35. And then in here, you can change the seating. If you hit Control S or Command S, and then save that file, then you can come here and click on this option, Reload Script, and then it reloaded the new geometry file that I just edited. And then to rebuild my mesh, I go through the same process, 1D, 2D, and finally 3D. And then it generated your mesh file from here. And then once you finish building your part, all you need to do is come here and click Save. And then it'll save your mesh file, which is your computational model with your geometry description, as well as your finite element mesh information. Are there any questions at this point?
Sorry, Miguel, can you make a specific refinement in a specific point, or how does it work?
So let me see if I understood the question. Is the question is if I can just refine a single point?
Yeah.
Yes, you can do that. I can come here and say 75 there, save it, and then come here again and reload my script, and then go through the same process. Now let me see. I will have to see and compare against the other geometry, but to compare the mesh, but that's how you do it. You basically, you can come here, or you can do it through your user interface, or you can come here and do the change yourself. Did that answer your question?
Yeah. Actually, I have other question. You can decide which element type can you put in your mesh?
That's a great question. And I believe This actually is going to show some of my noviceness with Gmesh, because I think Gmesh, well, I have used Gmesh only with for tetrahedral meshing. I think it has support for hex elements, but I myself have never used hex elements because Plato Analyze is a TET only finite element solver. So our physics are always solved with TET elements, and we have different types of TET elements, stabilized version, linear versions, depending on the physics. So I'm always using TET elements. So to answer your question, I know for sure they do tetrahedral elements. If you want a specific TET element that you want to use, then that depends more on the finite element code. In our case, we have support for linear TET elements, and we have another version that is a stabilized TET formulation that we use for plasticity problems as well as computational fluid dynamics. But hex element, I think Gmesh also has that support, but I have never used it myself.
Okay, thank you.
No problem. Are there any other questions?
Yeah, what's I noticed that that the beam file script only has geometrical information and nothing regarding the mesh. So when you open Gmesh, you have to click 1D, 2D, 3D every time, or how does that work?
If you open Gmesh with your geo file, then yes, it only has geometry information, so you will always have to regenerate the mesh. The mesh information is actually, let me go there. I just actually saved the mesh information, and I'm gonna bring my terminal window so I can show you where it is. In my case, it saved it in my home directory, which I think this is where I am. So this right here is the mesh file, and that's the file that has all the information about the mesh. So if I open that guy, here is the mesh information. Here is the connectivity information, all the node element coordinates, everything is here. So you can upload, the thing is that from the mesh file, I'm not sure if you can build, I'm not sure if you can build your geometry file from the mesh information only. So I think you will always have to upload your geo file and then rebuild your mesh. But the mesh file is this one.
Okay, thank you.
Are there any other questions? And actually, that's funny because I'm glad that you asked about the mesh file, because the file that we really need for Plato is this file. The geo file, think of it as Gmesh is providing the CAD interface or support. So you can create your geometry and create your CAD geometry using the Gmesh tools. So Gmesh has this geometry kernel, which is the one that I used and showed you to build your geometry. For Plato, Plato doesn't use the geo file. What Plato needs is the mesh file. So what Professor Hochhalter and myself need from you is the mesh file. So if you can use Gmesh to build your geometry and then go through the process that I just taught you and to construct your mesh, then you can save your mesh file here. You can click there, save it. And then in my case, it saved it in my home area with this name. You can assign names if you want. And then this is the file that Professor Hochholter and myself need to run Plato.
Does the geometry kernel matter if we use the built-in or the open cascade?
It doesn't matter because I think Gmsh is actually using Open Cascade under the hood.
Okay.
Are there any other questions? Okay, one more thing that I want to show you, and this is actually important, is, so once you have your geometry, remember we're going to apply boundary conditions and loads to surfaces. And for Plato to know on which surface you are, or you want boundary conditions apply or loads apply, we need to know the name of that surface. And for you to know the name of the surfaces and which surface that name pairs with, you can come here to this tool window and here this visibility window, and you can click this option, elementary entities, and it basically shows all the geometry entities that made your geometry. So here, if I apply, I see I only have one volume, so here's my volume. But if I want to see the surfaces, then that surface with ID 62 is the surface, and then you can keep going down and you can see the different surfaces. And this is important because with this, basically, let me come here. Plato, when we run the translator, and we'll check this for you, then there's no problem. But Plato, when he runs the translator that converts the mesh file into the Exodus file, he basically assigns names to these surfaces. And the names that are assigned are very simple. It's basically surface underscore and a number. And that number goes from 0 to the number of surfaces that you have on in your geometry. The order of that number is the following. It basically goes from the increasing ID number. So it goes in increasing order. So it starts with surface underscore 0 for this ID, and then subsequently it goes surface 1, 2, 3, 4, 5, 6, 7. You really don't need to know this information now because Professor Hochholter and myself are going to be running the problems. But in the future, if you find yourself working on your own and doing the translation yourself with our tools, then you can use Gmsh visibility tool and the awareness that Plato, basically the way he orders or names the surfaces are by assigning a name, and the name is surface, and then an ID to that surface, and that ID starts from 0, the number of 0, and it goes all the way on to the n number of surfaces, and is in increasing order based on your ID number from Gmsh. Just giving you some extra nugget here of information, but for now, you don't need to concern yourself with this. However, if you find yourself using the tool by yourself, you can watch this video again and see that information and kind of remember how that is done. And that's why I wanted to kind of show you this useful tool that they have. Any questions pertaining to this last nugget of information?
I got something really quickly.
Okay.
Is there when we were modifying the script, you had little commands like point, like line, extrude. Is there a resource for the list of all those different commands that we can use like that?
Oh yeah, the Gmesh website.
Oh, just the okay.
Yeah, if you go to Gmesh, they have a documentation, and they go over. Like if you really want to dive into those details, you can go to the Gmesh website, and then there's a manual. And then they have all that information here, geometry module, geometry commands, and you can see all of those here.
Okay.
It's fairly well documented. It's not like ours, which we're starting to document our tools now. But they have a pretty good documentation.
Okay. Thank you.
And let me actually put this in the chat window so everybody has access to that information. But yeah, you could actually follow, if you eventually learn these commands, you can actually follow, build your geometry model in its entirety here. If you wanted to, if you like that type of workflow, you could do it here. If you like the user interface, then you have this user interface to build your model. Are there any other questions pertaining to Gmesh? If not, then I'm going to now show you the input files. That's the other, so there's two files that we need to run Plato. The first one is the mesh file. We just went through a tutorial, a simple tutorial on how to build a geometry model and your mesh. And then the second file that we need is the actual input deck, which has all the Plato specific commands. And I'll start with the mechanical file or input file. So the file is pretty simple. We have made some progress over the past year to consolidate our input file. This time last year, I would have been very ashamed to speak to you about our input file situation, but we have made good progress this last year, and in March, we are going to release this fully supported input file that I'm going to show you, and with all the bells and whistles of access to all the physics and all the objective functions. Right now, the one that we have in our release branch is really nice to use, but it's limited with respect to the number of physics that you can access. Only mechanical, thermal, I think you can do thermomechanical, and maybe electromechanical. I think those are the four that you could do. And it's also limited by the objective functions or the design criteria. Not all of them are supported. But in March, all of them, everything will be supported. So CFD, mechanics with CFD, all of that will be supported through the input file. But this input file is fairly simple. There's multiple parameter lists or blocks. Basically, we have an objective block, and the word is fairly descriptive. This is where you define your objective function for the problem. Then you have, and I'll dive into the details of each one of them. But I'll first just give you an overview. And then this is your boundary condition block. And this is where you assign, like if we're doing mechanical problem, like a displacement type boundary condition. And then we have the loads. block, fairly descriptive. This is where you assign your loads. And then your constraint for the problem. In this case, we have a volume constraint. And then this is the volume requirement. And we have 30%. And then for this example problem, actually, we only have one block. So we have one material block. If you remember, there's only one volume. So there's only one block for one volume. And this volume is going to have a material. And that material, the details are in the material block. And you can see we're doing a linear elastic problem. So we have a Poisson ratio, we have our elastic moduli, and then we have the optimization block. And this is where we define the optimization parameters for the problem, like the type of optimization algorithm that we're using and other optimization related options. Then we have the mesh file. In the mesh file, this is where you assign you basically specify your computational mesh file. So as you can see, our mesh file has a format of EXO, which stands for Exodus. And basically what we're going to do is we're going to take the mesh file that you are going to build with Gmsh and run the translator so that we can convert that mesh file into an Exodus file. And that's what Plato uses to run. And then this block, I have it here, but really is defined for you by default. And it's basically saying that we have two codes that we're running, the optimizer and the finite element code. And these are the names of the executables. But this is auto-generated for you. But I wanted to at least describe what it was so you knew what that block stands for. So let me go into the details. So the details here for the objective block, there's a type. In this case, we are doing minimization of compliance with a volume constraint. Another way to describe that problem is to maximize the stiffness. So the type of objective that we're using is maximize stiffness. This low IDs keyword, basically, and then you see a number here. This low ID corresponds to the loads that are going to be active during optimization. And this number and this number should match. And why do we have that? I think last time Jose asked me if we could do, if you have multiple load, how do you do optimization and take all the load cases into consideration? This is how we do it. Basically, I could have, for this example, I only have one load, but I could have another load. And that load will have some other ID, and maybe that load is applied in the X direction.
Hey, Miguel, I got to interrupt you for a sec. Sorry. So now that it's 11:30, there might be some new students that have showed up. So if there are, please identify yourself in the chat about which room you want to go in, and I'll go ahead and apply you there. So I'll just give you about 5 seconds to identify yourself, and then I'll jump back to my room. Thanks, Emily. And Katie. Okay, Emily and Katie, is that? Oh, there we go. Nicolo, thank you. Go to ANSYS. Okay, going once, going twice.
Dr. Hochhalter, sorry, I'm in here twice. Can you add me into the abacus room on both the ones that I'm in here for?
Yeah, sorry, I should have seen that. I missed your other one. There you go.
Thank you.
Okay, all right, I'll get out of your hair. Thank you.
Thank you. So yeah, so basically you could have another load, and then you basically assign that load here. And what Plato is going to do is when he does the optimization problem, he's going to run multiple executables simultaneously. So both load cases, and he's going to compute the objective value for load case 1, and also he's going to compute the load case, the objective value for load case 2, and is going to add them together into one value, and then that will be the objective function value for the optimization problem, and it will keep going. What that will do is basically design a structure that that basically supports both load cases. So the geometry is going to be really different from a structure that was designed for just one load case. If you take both load cases into consideration, that's going to have an impact in your final geometry. So that's why you have this load IDs here, so that if you were to have multiple loads and you want to apply them independently of each other, but consider them as part of the optimization problem, then you can do it by using this loads IDs keyword. Are there any questions regarding to that point? All right. The same can be done with the boundary conditions. So in the boundary, actually, before I move on, basically for the loads, you can assign attraction and then the size set name. So this is, you see surface underscore 6. If we're using Gmsh, when Plato does the translation, he basically assigns surface underscore 6 for this face here. Well, actually, I created it in a different order, but in the model that I'm running, the surface here, the name that it was given was surface 6. For this model, it will be surface 2. But in my model, it was 6.
Quick question, why would it be surface 2?
Okay,
instead of 14?
yes. For this model, it's going to be surface 2, because like the way the translator works is it assigns the name surface underscore ID, and the IDs are assigned in the order of the IDs of Gmsh. So basically from, you see here the ID, the lowest ID is 1, and it goes increasing 10, 14, 18, 22, 26, 30, 62 in this increasing order. So following that order, what Plato does is it assigns 0, 1, 2, 3, 4, 5, 6, 7. So it's just basically following this increasing order.
With 0 indexing.
With
Okay.
0 indexing, yes, and it adds 1 after it.
Okay, thank you.
No problem. And then you have the surface name and then value. This is where you assign the X, Y, and Z direction for your force. And then load ID, you assign a number, any number that you want, as long as when you're running the optimization problem, this number that you use matches the number that you assign here. Now for the boundary conditions, you can do the same. For the boundary conditions, you can do the same game of having multiple boundary conditions and apply them in different ways in your optimization problem. You can do a different surface if you want, and then for those boundary conditions, it will basically run the optimization problem the same way I described with the multi-load case. It will do it independently, but build a geometry that satisfy both boundary conditions the way the problem is being described. Or you can assign them simultaneously as well, if you want. And if you have multiple IDs, then you basically, if you have multiple boundary conditions, you will do it the same way, like this. But for this problem, we only have one boundary condition. Then the code, you can assign, this is the name that we assign by default, is Plato Analyze. And then the number of processors, we're running this on one GPU in one node, in one processor. So you assign one. But if you were to run this problem on multiple GPUs, then you will basically add different numbers and you can run bigger problems on multiple GPUs. So kind of describe this too. For the constraint block, it's fairly straightforward. You basically have type, and then what type. We support multiple constraints. For this problem, we're going to do volume. But if we were doing stresses, then we will put stress here, or only displacement if we were constraining displacements. But there's many options that you can choose from. But for this problem, we did volume. And then what is the volume fraction? And then this is the target value. And here is your target of 35% of the total volume. The block basically, it relates to, like I said earlier, to the volume. So in this problem, we have one volume. This is the volume, and we're going to assign one material to that volume. If you were to have another block, then you will create another block, and then you can use the same material, but you can think of having another material. Maybe you have another material here with different material properties for that volume of material. And in that case, you will do it like this, where you create another block or volume for each block. You need to assign a material to that volume. This is how you do it. Another question that you may have is, let's say you have a block of material that you want the optimizer not to optimize at all, but is part of the simulation. The way to do that is as follows. Let's say we have another block of material, and we have another ID, and that block has the same material properties as block one. However, you do not want to optimize this block. You want that block to stay frozen throughout the optimization. So what that means is that the optimizer is not going to remove any material from that block. So the way to do that, there's a keyword that you will put in the optimization block, which is fix. And then you assign here the ID of the block that you want to be fixed or frozen. So then the optimizer now knows that you have three volumes, volume 1, 2, and 3. Block 1 has material 1, block 2 has material 2, and block 3 has material 1. However, block 3 is non-optimizable. It should be frozen and the optimizer should not touch it at all. And what the optimizer is going to do is remove material from block 1 and block 2, but it's going to keep block 3 frozen. and it's not going to remove any material at all. And this is how you do it. And you can have more blocks here. You can have 4 or 5. You can have as many blocks as you want frozen. But that's how you would do it. Are there questions related to that?
How does it know which part of the volume gets associated with block 1 or with block 2?
Good question. So the translator is going to be the same as with surfaces. If you were to have more blocks or volumes in your model, then you will have volume 1, 2, and 3. The translator will convert those into block underscore 0, 1, and 2. And the order is going to be increasing order, the same as the surface use case.
Okay, makes sense.
So that's how it will do it. And then you can come here and use Gmsh to basically guide you on your process, because kind of seeing block, this is volume 1, this is volume 2, this is volume 3. And I think I have an example of a heat sink that Carter, I don't know if Carter, I think Carter is here.
Yeah, I'm here.
Okay, yeah. So Carter emailed me a heat sink, and he has 2 volumes. And one of those volumes, volume 2 in his case, is frozen. So for his use case, he will basically have 2 volumes, and then the second volume will be fixed here. And I hopefully by the end of the class, I can, maybe if you stick around, I can show you that example. But this is how you do it. And now the optimization block is fairly simple. There's not a lot that you need to do here either. Number of processors, we're using 1 GPU, 2 GPUs. In this example, we're using 1 GPU. The optimization algorithms, they also run on GPUs. Or if you're doing MPI, then you will have 2 or, I don't know, 200 processors, as many as you have access to. In this problem, we just did 1. Then this filter radius is, if you're familiar with topology optimization, the problem that I solved here, and I'll show you the results, I was using what is known as a density technique, a density discretization technique. There's also level sets, which we support. But if you're using density methods, filters are often used to avoid numerical instabilities in your solutions. If you use a commercial tool in the past, you have seen that when you run your topology optimization problem, sometimes, and if you were to plot the topology, you see that the topology is not as a homogeneous 1 number, like a solid 1 number. It varies between 0 and 1. And you have values that are between 0 and 1. And usually what you want is a fairly discrete problem where most values are 0 and 1. The filter is used in topology optimization when you have discretization methods, density methods, to force the values of those densities to 0 and 1. So you can actually have a very sharp geometry and description of your geometry. So that filter, and then the way the filter is applied, you have a what is known as a region of support, a circle of support, and there's a radius. And the filter, the bigger the radius, usually the smoother your results are going to be. The smaller the radius, the coarser your, the bigger the radius, basically you can use it to control how small the features that the topology optimizing is created are. So if you have a big filter, the smaller features are going to be avoided. And if you reduce your filter, you're going to have smaller features in your geometry. So you can think of the filter as a way of controlling your feature size on your part. So that's how it's done in topology optimization. And all the codes are there. They're using some sort of filter. And for discretization methods of density, we use a filter too. Any questions related to the filter? All right. So the number of iterations for the optimization algorithm, you can assign it in here by using this keyword. This output frequency keyword is, you're not going to use it, but basically we use this keyword for the user interface. If we have the user interface, Plato will output STL files every n number of iterations, optimization iterations. So if I were to put this at 5, then Plato will output an STL file every 5 iterations. So that's how we use this key, or this is why we use this keyword for. But for your case, you can disable that by just assigning a number that is much greater than, or greater than the number of optimization iterations, and then the STL files are not going to be output. And then the algorithm, this is where you assign your optimizer. There's like 10 different options that we have, but this is where you will assign the algorithm. Discretization, there's 2 options, either density or level set. Our level set product is going to be released in March. So right now in the release product, we only support density, but level set is will be there in March in the release product. But this is the keyword is used to tell Plato, am I using a density method technique or a level set technique for my topology optimization approach. This initial density value is basically used to set the initial value for your density field for your topology to start the problem. Usually you assign it to the same number as the volume constraint, this volume fraction. So 0.35, but really doesn't matter. Plato will solve the problem regardless of which number you put here. Usually we put 0.5 by default, but you can play with that number if you want. And I think I already described this keyword in this as well. This is fairly descriptive. So that's it. That's the input file. It's not, it took me some time because I wanted to go over it in detail, but it's not complicated. It's really, this is it. Are there any questions?
I have a question on the material.
Yes.
Does it just support, I guess, isotropic material? We just have a, for example, like a transversely isotropic.
Yeah, we have anisotropic materials. We support. Actually, let me show you an example. Let's see. I know I have one here that I put myself. Analyze, compliance, ortho, here. But I don't have the SNL generator here. But the answer to your question is yes, we support anisotropic materials. It's funny because this SML generator, this input file that I'm going over with you, what it does is when Plato runs, it generates all these other files. This SML files is basically, are all the input files that really Plato needs to run. And there's technical reasons behind all of that, but they are all generated from this file. So I don't have if you're interested, I can set up an input file. I actually have it on my machine, on my work machine. I have an input file that is using orthotropic materials, and I can send that to you.
Okay, yeah, that'll be interesting to see. I'm not doing it for this project, but for another project down in the future. So maybe I'll get your email and we can exchange that.
Yeah, just please do, because we support orthotropic material. We support homogenized material properties. Like you can input the tensor, the full tensor for your material, and then Plato will use that as your material model for the topology optimization. Obviously, we support thermal material models, either linear or nonlinear, because we support temperature-dependent material properties. For the CFD, we support material models that are used for those. Yeah, so we support more than just linear material models. Other questions?
I've got one.
Yes.
So in this example, we have a fixed boundary condition and a traction load.
Mhm.
What other kinds of loads or kinds of boundary conditions are supported, and what's the keyword associated with them?
Okay. For for mechanical, we have traction and we have pressures. You can apply a pressure. So if you were to apply a pressure, you basically put pressure there. And then the same thing is, then everything else is the same except value. In value, for a pressure, you just need a number. And then you will put the number for that pressure. And then this is how you would do the pressure but load. So we support pressures and traction forces for mechanical problems. And when it comes to boundary conditions, if it's a mechanical problem, we support a fixed displacement, or you can do fixed displacement and then no set name surface, and then you can do value if you have a prescribed displacement of 0.1 or something, then you will do it like that. And let me see what other, so we have fixed displacement, you can assign a prescribed displacement. We also do time-dependent loads. They're not supported yet in this XML file. In March, they will be added. So right now we do not have support through this, but the code supports time-dependent loads as well. So if you're doing a mechanical problem, you can input either a text file with the loads per time steps, or you can input a function, and then Plato internally will compute the value of the load based on the time step. So those are for mechanical problems. Are there any conditions, either loads or boundary conditions, that you have in mind?
Well, and for my problem, I actually just need fixed, and I need a pressure, so this works perfectly.
Okay.
But yeah, I was just thinking of maybe like if I wanted to allow for rotation in certain directions. I don't know if that's possible.
Oh, okay. Yeah, right now we do not allow for like centrifugal forces, those type of conditions, or forces or rotation boundary conditions and such. Yeah, we don't support that right now.
And one last thing, what if I wanted to comment something on this file? What's the character that you use for commenting?
That,
Got it. It's like C++.
yeah, like this.
Okay.
Other questions? Well, let me show you some results, because I think I didn't show you any. I'm being like talking here and showing you words, let me actually show you some results. So to visualize your results, you can basically do it in ParaView. ParaView is open source. It's a very powerful visualization tool, and it's developed as Sandia, and you can visualize the results from Plato in ParaView. So the way we do that, I already ran the problem and I have the results here with me. So I'm going to show you the output from the optimization problem. So the mechanical problem, I'm going to load that guy. So I just uploaded the file. You see it here, mechanical.xo, that's the name of the file. And then I'm going to visualize all the variables that I have. You can visualize displacements, stresses. I didn't do it for this example. I can show you how to do it later. So once you select all the variables that you want to visualize, you click on the apply button. Now here you see the geometry. I did a minor, just a slightly different geometry that you guys did, that we did here, constructed, but it's the same one more or less. So there's your geometry, and then if you want to visualize the topology, the actual topology, here you see the topology keyword, click on that. There's 50 iterations that we did. So in a way, you can kind of see the topology optimization results. Actually, let me do something. It's actually better to see it this way. So this is your density field. You can see blue is empty or void. Red is the actual topology. But to better visualize this, you probably want to construct the ISO surface so you can actually see the geometry. To do that, ParaView has a really nice tool. You come here to filters, and then you come to the alphabetical order option. And then we're going to come here down, and then there's this ISO volume option. ParaView has a lot of things that you can do with it. You can build histogram, you can build so many different things, you can plot things, but again, you can learn if you're really interested in that. ParaView is open source, documented, and you can learn more in their website. But for our case, what you want is to select this ISO volume option. And from there, you want to construct the ISO volume or ISO surface for the topology. So you select topology here, and then we're going to select the values that are above 0.5, but you can play with that number if you want. Our geometries come out fairly crisp, so you don't need to play with that number that much. But this is the geometry. This is the mechanical optimization problem. And here you see the results. So you see it was fixed on this end, and then we had a traction load that was pulling on this cantilever beam. And this is what Plato built. And if we were to do just iterate over time, you kind of see how Plato constructed the geometry. I think this problem, the one that I ran, had 300,000 elements, and it took like 40 seconds or less to run on a Bolt GPU that I have. So you can see Plato quickly gets to that geometry. So it's fairly probably after, let's see, 20 iterations is clearly there. Then after that, it's just doing some fine tuning, but it gets there fairly quickly. There's not a lot of work that needs to be done.
Did you run this with your something like an HPC or just a personal computer?
I did this on a laptop that has a Volta GPU. So I have a laptop, and then it has an NVIDIA GPU, and I ran it on my laptop.
How do the RTX chips compare to the Volta GPU? I'm not sure.
So RTX and NVIDIA. So is this the RTX?
2060. That's what I'm just wondering if I need to use the HCPC for the stuff I'm doing, or if I can just use my personal computer's processors.
Okay, so do you have an NVIDIA GPU on your machine?
Yes,
And which one is it a Quadro
it's an RTX 2060.
2060? So it will run just fine. How many megabytes or how many gigabytes of memory it has?
16.
16?
Yeah.
Okay, so you can probably do as big as 2 million elements, and it will do just fine. The Voltas are a bit faster because they're later generation than the RTX GPU, but it will run just fine. Actually, my colleague has a RTX Quadro GPU on his machine, and he runs problems, and he doesn't have any problems. We support any GPU that is compute capability 26 or later. You should be able to run it.
So we could just go to the Plato website and get the open source, compile it in our own machine, download peer review Gmesh, and be able to do all this stuff on our own local machines then? Okay.
Yeah, you should be able to.
Okay, thank you.
But yeah, here are the results. And actually, I'm going to show you the thermal problem as well. First, I'll show you the input file. Input file, I don't have to go over it in detail as much as the other one because it's really the same input file. The only difference is that we have different quantities of interest, but it's the same format. So we have a fixed temperature. So by fixed, basically that means that the value is 0. And then we have a load at heat flux that we are applying on this surface. And then the temperature is set to 0 on this surface here for the problem. And then we're trying to maximize heat conduction as our objective. And we have the same constraint. We have a volume constraint with the same mass budget as the mechanical problem. We have one volume, one material, and our material model. It's funny because we're not doing a transient problem. So we're doing steady state. So those two are really not needed for the problem that I ran. We only need the thermal conductivity coefficient for the problem. If you were doing transient, heat conduction, then you will need your material density and your specific heat coefficient. But for this problem, we're not doing transient. Therefore, you just need the conductivity coefficient. And then the optimization parameters are the same, except that I ran it with a different optimization algorithm. And if you know topology optimization and are familiar with the literature, I'm sure you know what MMA is. We have our own MMA version. It's parallel, and it can run on either CPU or GPUs. So it's fairly spiffy. And that's it. That's the input file for the thermal problem. Are there any questions?
So if we wanted to do, just going back to the mechanical problem, I don't know if anyone has questions about the thermal, but for the mechanical problem, if you wanted to do the optimization based on, I think for the previous one, it was mechanical, it was stiffness. What if we wanted to do mass optimization? Is that possible?
Yeah, so, and what, so is it mass with, do you have any specific, because if you were to do just minimize mass, you need a constraint, because then the optimal solution will be zero mass. So we will have to constrain it with something.
Oh, I was, well, the reason I'm asking this is because I noticed that the materials you specified don't have the density associated with them.
Okay.
And I'm guessing at some points you want to include the density if you want to take that into account. I'm not sure if I'm
Okay.
asking the right question, but.
No, you are. Then what, so for example, for the stress problem, basically the formulation is minimize mass with your stress constraints. And basically for that problem, let me bring up the mechanical option again. Yes, you need density here. So you will specify density there, 1 to the 3. And then for that problem is, I think the keyword, since we're changing the keywords right now, I'm getting my head confused a little bit, but I think the keyword for the stress one is minimize mass, and then stress constraint. So for that, and then you don't need a constraint for that problem, because from this information we know that we're minimizing mass and we're constraining stress. So then for that problem, then yes, you need density. So you will need density here, and then the type of objective will be minimize mass with stress constraint. And then that formulation uses density and minimizes the actual mass. If you want just the mass, then you can do, let me go back, constraint, minimize mass. You can put type mass there. And then we need a constraint here. In the new version of Plato, this will be allowed, like stress. But right now, the one that I'm showing you right now that is in the open source doesn't support this format yet. But here you can put, I think you can put displacement there, and then that will work.
So then what's the difference between doing the type minimize mass stress constraint and the type maximize stiffness? What's the difference in the results?
Oh, so those results, if you remember the tutorial, let me see if I have the, do I have the presentation? If you remember from Tuesday, when we ran, I showed 2 examples for an L bracket. And the L bracket, there was one that was actually maximizing the stiffness with a volume constraint. And the re-entrant, there was a stress concentration in a corner.
Yeah, I remember.
And it didn't remove that stress concentration. It basically kept it there. And then this mass minimization with stress constraint, it actually smoothed out, rounded that corner and removed the stress concentration.
Okay, so when we specify the stress constraint, do we have to give it a threshold, or does it just try to minimize it overall?
Yeah, so you have to give it a threshold. Oh man, I wonder if I have If I were in my laptop, I can show you the input file. Let me see. I don't think we have an SML generator here version. Let's do something. Send me an email and I can send you an example of an input file for that problem, the stress constraint problem with mass
Okay.
organization.
Okay, yeah, that'd be great. I can just put it in the chat and
Yes.
that probably works.
Yeah, and I'll send you an input file for that problem, so I don't get my wire cross here. And what I'll do so that everyone here has access to it, what I'll do is I'll ask Professor Hochholter to upload it to the class website. Anything that I share with other students here, I'll ask Professor Hochholter to upload it to the class website so that everybody has access to it. So are there any, let me show you the thermal results actually before so you can see those as well. Same geometry for the thermal problem, but for the thermal problem, what we did was we apply a thermal flux here, a heat flux, and then we wanted the temperature to go from the temperature that was seen, the high temperature that was seen here on this surface because of the heat flux, all the way to 0 on this end. So that's the problem that we're trying to do. And at the same time, we're trying to minimize the weight and maximize the heat conduction from this end to this end. So let me show you the topology that we got. You cannot see it well there. So if you remember, we go to the filters. This is fairly convenient here. You can come here after you use the ISO volume for the first time. You can actually come here and then in recent, and you can see your recent options or filters that you have used. I have the ISO volume there, so I could pick that one. But just to refresh everyone's memory, I'll go the long route. So alphabetical, scroll down here, my ISO volume, filter is there. Want to filter the topology. And I want to include the values that are above 0.49. Apply. And that's the topology right there. Fairly interesting. So same geometry, we just same mass requirements, but we just ask the optimizer to do different physics. And if we compare one versus the other, let me come here and modify the color. So if you compare two different geometries. Now, for me, what will be really interesting, actually, I'm going to do this next, and I'll share the results with you. I didn't have time to do it for the class, but do a thermomechanical simulation, because here you're seeing the mechanical solution and you're seeing the thermal solution. What happens when you have both together? If we do thermomechanics, I'm assuming it will be a union of these two geometries, but it will probably be different, but you kind of get an idea of what it's trying to do. Do you have any questions? Let me run this so you kind of see the geometry generation in time. So as you can see, I did 50 iterations, and I had a very tight stopping tolerance, but really this was done fairly quickly. Like I didn't need to do as many iterations. Like after, again, probably 20 iterations, I was there. So do you guys have questions for me?
I've got a quick one. So from Gmesh, we get the geo file and the mesh file. How do we turn it into XML?
Great question. We have a translator. In that translator, we have a script that does it. So let me come here. Then you see Python scripts, mesh to SO, EXO. This Python script does it. So basically, we run this Python script, and the way the Python script is ran is as follows. Right. You basically do your mesh to EXO, and when you install Plato, the executables for the translators are going to be in a bin directory somewhere in your machine where you install Plato. And I think, well, let me finish this thought. Basically, what you have to specify is the path to your bin directory, and then the name of the file that you want to translate. And then you run that command, and that's it. I have a video that I did myself that I'm going to upload, that I'll ask Professor Hochhalter to upload to your class website that shows how to do this.
Okay, yeah, because it's this step, and then actually using the terminal to have it run Plato. Those are the few steps I'm missing to.
Yeah, so I have a tutorial video for that I did myself. So I'll ask Professor Hochhalter to upload that guy to the website. And all of this in the open source, sadly, right now, since we don't have the user interface, you have to rely on the terminal. So this is why Professor Hochhalter and I are asking you to maybe build the model yourself, and then we can run them for you, so that you don't have to run this additional step.
Oh, that's not bad. I don't get scared by terminals.
Okay, so if you're familiar with that workflow, then by following the steps on the tutorial, then you can do it yourself.
Okay, that sounds.
Let's see. So let me do something here. If you give me a second here, let me see if I can find something on my personal computer that I want to share. So give me like a couple of seconds, maybe like 30 seconds or so. I apologize.
No worries.
Okay. All right, I'm back here. So let me see. I think there was one example. Actually, before I jumped in, does anyone has a question about the input files, or I maybe thought that I could set up an input file for the heat sink problem. I think Jake asked me to try it. All right. So let me try to do that. I wish I was in my work computer, because I can run problems and I have access to more things. Well, let's see. I think the tutorial for this problem, thermal. Where is it? Document. Oh, okay. Gmesh. Where is my? Huh. I know I have it here somewhere. Oh, here it is. So, Carter, are you online?
Yeah, I'm here.
Okay. So I was looking at this problem, and I had a few questions for you.
All right. You can look at my beautiful paint diagram there.
All right, there it is. So this is a heat flux that is applied on the bottom.
Yep.
All right, so we have a heat flux here, and then this base region is frozen.
Yes.
Okay.
Correct.
And then this H is, what is H for you?
Basically, we're just assuming some constant, maybe like 50 watts per meter squared Kelvin, something like, basically just the heat transfer coefficient
Okay,
of the air around the top of the heat sink.
okay. And what is K?
The thermal conductivity of the material. Yeah.
All right, thermal conductivity of the material. So you want to, do you want to do first a thermal problem? Like what type of problem you want to do here? Because we can go on multiple levels. The easiest level will be, well, we can do first a steady state thermal problem. We can apply the heat flux. We can have a thermal conductivity. I don't know if there's an additional temperature that you want to meet. Are there any temperature boundary conditions here?
No temperature boundary conditions. It would more be like a convection boundary condition, if that's even possible.
Okay. Oh, so like an initial velocity, like an initial. So if I were to look at it, so initial convection. So when I hear convection, I think of some flux.
Yeah. Yes.
So do you know? So let me maybe ask you this: if you were to do, what was your plan for this problem? Like if you were to do this problem yourself, what type of topology optimization problem you will want to do?
So I guess I can give an example. So we've solved a simple example of this problem not using topology optimization, using COMSOL. So where we would define the, just doing a steady state thermal problem, where we would define the base with a constant heat flux, and then we would define the heat sink region. So in this diagram, all the surfaces of the heat sink region would define that with a convection boundary condition, meaning just Newton's law of cooling.
Mhm.
So where Q is proportional to H times delta T.
Okay. Okay. All right. Okay, and then those boundary conditions, are they apply on the surface, on the faces?
Yeah, so obviously with this geometry, they would be applied to the surfaces. I guess it gets a little confusing given that once your topology changes, then your
Mhm.
surface would also change.
Yeah.
So I don't know if you can like define boundary conditions on a volume and then use elements, surface elements within that volume. If you can define those as your boundaries, I guess it's a little bit convoluted there.
Okay. With level set, that wouldn't be a problem, because with level set, what we do is, yeah, you can start on those surfaces, but every time the geometry changes, we're actually building a conformal geometry of the topology optimized geometry. So with density methods, it will be harder to do the convective boundary condition, because then you need to project, and we don't have that. That would be, yeah, that would be problematic. But with level set, yeah, that won't be a problem. Okay. So basically you have steady state, you have Q, and it's changing the geometry. So let me ask you then, and this, I'm learning here with you. If you were to, are there any other options to the convective boundary condition that you had thought about? If you were to have that difficulty where if you're doing topology optimization with any of the commercial software, you'll have that problem where you are not going to be able to do that convective boundary condition.
Sorry, what was the question there?
Well, so if you were to do topology optimization,
Yeah.
if you're going to do topology optimization and you have this convective boundary condition where Q equals H delta T, and it's applied on the surface, but if material is removed, the surface is changing. And now that convective boundary condition needs to be applied to the new surface. So that is what you have described.
Yes.
Yes. The problem is that you are not going to be able to do that with any commercial software, because they don't have the capability that you want, which is, as my topology optimizer is changing the geometry, I have this Neumann boundary condition and I need to project it to the new surface. So that will be a problem. Yeah, you will have that problem. So my question to you is, have you or your team thought of maybe another way to do this? And I'm really curious and asking, it's something that I have not done myself.
If I could jump in, maybe we could try to maximize the surface area.
Okay, yeah, that's a good one. Yeah, maximize the surface area. And maybe, do you want to increase conduction? in the heatsink? What other things you would like to do?
Yeah, I guess maximizing surface area and conduction in the heatsink would sort of achieve a similar goal, I guess.
Okay. The reason why I'm asking is I'm really curious about the problem. And then second, I'm kind of thinking in my head, okay, with what we have right now, how can we solve the problem? So you can kind of get going. So we can maximize surface area, that is there. We can maximize conduction, that is there. You can apply the heat sink. You have H, you have T here. Yeah, I think you can get I think you can get going with that problem actually. If we were to start first, and then we can learn from the initial iteration. But if we were to start with the geometry that you have here, we apply this flux at the bottom, and then we have the material properties, and then we try to maximize surface area and conduction, and then we can put a constraint with about mass. Then yeah, I think that will get you going, like at least a first iteration, and then from there we can learn and see how can we adjust.
Yeah.
Because ideally, probably what will be ideally for you is to also do like a convection diffusion problem, where now you have a transient physics, and you have convection effects, and you also have the diffusion effects, and you have all of that in your problem. That's ideally what you want to do. Is this forced convection or natural convection for the heat sink problem?
This one's forced convection.
Yeah, okay. So if it's forced convection, then yeah, that will be the ideal one. And I'm like a month and a half away from, or maybe less, I want to say a month, from having the convection diffusion physics in place, so that you can then move to the second level, which will be let's do the forced convection and transient effects, and let's see how this change the problem. But to start, we can start with steady state as you described, the heat flux, maximize surface area, and then maximize conduction with some mass budget, and then that will get you going.
Cool. Yeah.
Okay.
That sounds like it is a pretty good first step, I think. And that the time frame on the forced convection convection diffusion problem you're talking about, that actually seems really good for us. So definitely if you could update me once you have that figured out, that'd be great.
Yeah, I'll do that.
Thank you.
And I think with the geometry, so I have your geometry. I can set up the problem and run it and see what happens. Because I'm interested. This is actually a really interesting problem, and I know there's a lot of people interested in this problem besides you. There's like designing heat exchangers, heat sinks is a must.
Yeah, no, for for sure. Were you gonna set that up live right now? Is that
right now I can't. I wish, because I am on my personal computer. I'm not on my work computer, so I cannot set it up right now.
okay? Yeah, that's fine.
But I can set that problem up as well in the input file, and this is why I wanted to kind of talk to you and ask you what was the problem, because then I can set up the input file, and that also can be uploaded onto the website.
Okay, awesome. That's that'll be very helpful.
Yeah, I can definitely do that. And that should be, geometry is fairly straightforward. And yeah, that I can do. There's even there's like 3 layers or 3 tiers to this problem. It could be steady state with just the heat equation. Then you can do transient with just the heat equation, so just diffusion effects. And then once I have the convection diffusion, then you can go and all the way. Those are, so the first 2 tiers are available, are there. So we could explore those 2 options first and then wait for the last one.
Yeah.
All right.
Awesome.
All right. So do you have any, do you have documentation for this problem?
Did you just get the files, or did Dr. Hochhalter forward that email that I sent him?
I only got, oh, maybe, well, let me see actually, before I throw Dr. Hochhalter under the box.
Because otherwise I can just forward you that email and it has some actual textual descriptions besides this diagram.
Yeah, what I got was, I got a zip file with the mesh file, the geo file, and the image that I'm sharing here with you. And yeah, Sandia, so if you can send that to my personal email, because Sandia, what happened was that Sandia blocked your email because he had an attachment.
Oh, gotcha.
And I didn't get your email with all the bells and whistles.
Okay, yeah, I'll forward that right now to you.
Yeah, because then I can read it and from there kind of learn more about this problem and then get a better intuition into the problem. So I think right now, sadly, I think that's all I have for you guys, because right now I'm fairly, my arms are tied because I cannot run problems and play with different options and do anything because I'm not allowed to use Zoom on my laptop from work. So
All
if
right,
you
well,
have,
thanks for your time.
yeah, if you have any questions now, I'll be glad to answer them. If you have any more. All right. Okay, so I'll basically have a few notes here. Stress constraint problem. And then also the steady state heat sink problem. All right. And I think those were the 2 problems that people asked for. So what I'll do, I'll create those input files and upload them. Ask Professor Hochhalter to load those to the website, so you have access to them. And then I'll see if I can run this problem here. All right. Thank you all for your time. I appreciate it, for your interest as well. And I hope I can continue to interact with you in the near future and help you with your problems.
Yeah, thanks for helping us all out. It's very helpful having a developer of Plato set up all this for us. So
Yeah,
Yeah.
thank you. Thank you.
Thank
It
you.
was really
Yeah, thank you.
informative.
No problem. Oh, and then the other one was Jose. Now I remember the tutorial for the mesh to Exodus. All right, that's the last one.
The tutorial for that, and if you have one for actually accessing Plato and getting that final, what kind of file does Plato output?
Yes, great question. So I can show you that now. I think we have the results here. So let me see.
Because that would be the file that you put into pair view, right?
Yep, that's correct. If it's not here, I can write it down because I know it from the top of my head. See, yeah, all right. Basically, Plato, I may have one here. See, do I have one here? No, but it's okay. So basically, the file is Plato main dot exo dot 1.0. That's a file, that will be the output file that then you will upload to peer review.
Okay, and that's a weird extension.
Yeah, it's weird because it's the domain decomposition tool adds the number of processor that it was partitioned. But yeah, we're fixing that on the next release. Next release, it will be just output.exo, that's it. But yeah, it's a weird extension. And actually, that's actually a good point. When you come to peer review and you come here to upload the file, you just click open. And then since it doesn't have an extension that it recognizes because of the weird 1.0, you have to come to here, files of type, and then you see all the different files that Exodus supports, but then you hit all files. And then by doing that, you can see all the files in your directory. And then you'll see this guy and you'll be able to upload it.
Okay, and we would see for example, exo.1.0, and that's the file we open. Okay.
Yeah, you'll see Plato main .exo.1.0.
Okay, sounds good.
Yeah, and then you just upload it, and then you'll have it here. But yeah, that's a really good question.
Okay, I think that's all the questions I have, at least for now. I might shoot you an email if I get stuck on something complicated, but.
All right, so here is my email too for you guys. So you have my personal one. You can email both. Sometimes I close my email and I'm working and then I turn it on, and usually I'm more connected to my personal email. So you can use both, whichever. You can CC both emails if you want. And then I'll be sure to get it. Also, there's, you can email everyone in the team by using this email. So you can do that too.
Okay,
then-
I don't think my problem is complex enough to email the entire team, but yeah, that's helpful. Thank you.
Yeah, it doesn't matter for us. I think sometimes it's actually sometimes good to have everyone, because if I'm not available or I'm traveling or something, then someone in the team can see it, and we all are very helpful. So yeah, don't hesitate to include everyone in the team.
Okay, I'll keep that in mind. Thank you.
Yeah, no problem. All right, guys. Now let you go. Have a good one.
Thank
Thanks.
you again for everything.